Imagine buying 10 liters of gasoline, costing 7 liters away before your car even starts moving. That sounds impossible, but that's surprisingly close to what happens inside many gasoline engines. So why did the world rely on them for over 100 years? And why are electric cars suddenly replacing them almost everywhere? Gasoline cars transformed the modern world. They built highways, connected cities, powered economies. For more than a century, they seemed impossible to replace. Yet today, almost every major car company is racing toward electric vehicles. Governments are rewriting transportation policies. Battery factories are appearing across the globe. Charging stations are spreading faster every year. So, is this really about saving the environment? Is it about lower fuel costs? Or is there a much deeper engineering reason hiding underneath the hood? Because once you understand how both types of cars actually use energy, you'll never look at a car the same way again. Every time you press the accelerator, something remarkable happens. Inside one vehicle, tiny explosions push metal parts thousands of times every minute. Inside another, invisible magnetic forces quietly spin a motor. Both move people down the same road, but they do it in completely different ways. And those differences are reshaping one of the world's largest industries. Today, we'll discover why electric cars are replacing gasoline cars, not just because technology has changed, but because physics has always been pointing in this direction. It may sound surprising, but electric cars are actually older than many people think. In the late 1800s, electric vehicles quietly drove through city streets. Some were cleaner, some were quieter, and many people actually preferred them over early gasoline cars. So why didn't they win? The answer wasn't that electric cars were worse. The world simply wasn't ready for them. At the beginning of the 20th century, roads stretched farther every year. People wanted to travel longer distances. Gasoline contains an enormous amount of energy in a relatively small amount of fuel. A quick stop at a fuel station could keep a car moving for hundreds of kilometers. Then came one invention that changed everything: the electric starter. Before this, many gasoline cars had to be started by turning a heavy hand crank. It could be difficult and sometimes dangerous. Once electric starters became common, gasoline cars became much easier for ordinary people to drive. At nearly the same time, huge oil discoveries made gasoline inexpensive and widely available. Fuel stations spread across cities and highways. Repair shops appeared almost everywhere. Factories learned how to build millions of nearly identical engines. Within just a few decades, an entire transportation system had grown around gasoline. Roads, gas stations, mechanics, supply chains, refineries, everything supported one technology. Electric cars didn't disappear because they couldn't work. They disappeared because gasoline had already built the world around itself. But underneath all that success, a hidden weakness remained. One that engineers have been trying to solve ever since. Hold up, if gasoline became the global standard, why are engineers now trying so hard to replace it? The answer begins with something almost invisible, and that is energy. Every drop of gasoline stores chemical energy. When the fuel burns, it creates tiny controlled explosions that push pistons up and down. Those pistons spin a crankshaft, which turns gears, drive shafts, and finally the wheels. But every one of those steps wastes a little energy. Some escapes as heat from the engine. Some disappears through friction between moving parts. Some leaves as hot exhaust gases. By the time the power reaches the wheels, only about 20 to 30% of the fuel's original energy is actually moving the car. And the rest has been lost along the way. An electric car takes a very different path. Instead of burning fuel, electricity flows from the battery directly to an electric motor. Inside the motor, magnetic fields pull and push a rotating shaft. No explosions, no pistons, no exhaust, far fewer moving parts. That simpler design means much less energy is lost before it reaches the wheels. Modern electric drivetrains can convert more than 75 to 90% of electrical energy into motion, depending on operating conditions. But efficiency isn't just about using less energy, it's also about recovering energy that would otherwise be wasted. When a gasoline car slows down, its brakes turn motion into heat. The energy disappears into the air. An electric car can do something different. As the wheels slow, the electric motor briefly becomes a generator. Instead of wasting all that motion, it sends part of the energy back into the battery. It's called regenerative braking. Think of it like catching part of a bouncing ball instead of letting it roll away forever. You don't recover every bit of energy, but recovering even part of it adds up over thousands of journeys. So if electric motors are this efficient, why didn't they replace gasoline engines decades ago? The answer wasn't the motor. It was what powered it. It is the battery. For over a century, batteries held electric cars back. Early batteries were heavy. They stored relatively little energy. Charging took a long time, and they couldn't take drivers very far. They were so heavy with limited energy. Everything began to change in the late 20th century as engineers improved lithium-ion batteries. Lithium is one of the lightest metals on Earth. Its chemical properties allow batteries to store much more energy for their weight than older technologies. That meant one simple but revolutionary improvement. Cars could travel farther without becoming dramatically heavier. Battery management systems also became much smarter. Modern electric vehicles constantly monitor the temperature, voltage, and health of thousands of individual battery cells. If one area begins to overheat, the system adjusts automatically to protect both performance and safety. Fast charging also improved dramatically. Instead of waiting overnight, many modern electric vehicles can recharge a significant portion of their battery in roughly 20 to 40 minutes at high-power fast chargers. Although the exact time depends on the vehicle, battery size, and charger, every year, engineers continue improving batteries. Some focus on increasing driving range. Others reduce charging times. Others lower manufacturing costs. And researchers are already developing the next generation of batteries, including solid-state designs, which could store more energy while improving safety and longevity. The battery wasn't just improved, it transformed what electric cars could become. But another question still remains. If electric cars are becoming better every year, why are some people still hesitant to buy one?